It is undoubtedly unintuitive that water flows in the soil and rock below our feet. A 1904 Texas Supreme Court case famously noted that the movement of groundwater was so secret, occult, and concealed that it couldn't be regulated by law. Even now, the rules that govern groundwater in many places are still well behind our collective knowledge of hydrogeology. So it's no surprise that misconceptions abound around water below the ground. And yet roughly half of all drinking water and irrigation water used for crops comes from underneath the surface of the earth. You can't really look at an aquifer, but you can look at a model of one I built in my garage. And at the end of the video, I'll test out one of the latest technologies in aquifer architecture to see if it works. I'm Grady, and this is Practical Engineering. In today's episode, we're talking about groundwater and wells. This video is sponsored by CuriosityStream and Nebula. More on them later. Not all water that falls as precipitation runs off into lakes and rivers. Some of it seeps down into the ground through the spaces between soil and rock particles. Over time, this infiltrating water can accumulate into vast underground reservoirs. A common misconception about groundwater is that it builds up in subterranean caverns or rivers. Although they do exist in some locations, caves are relatively rare. Nearly all groundwater exists within geologic formations called aquifers that consist of sand, gravel, or rock saturated with water just like a sponge. It just so happens you're watching the #1 channel on the internet about dirt, and there are a lot of interesting things I can show you about how aquifers behave. I built this acrylic tank in my garage to illustrate some of the more intriguing aspects of groundwater engineering. I can fill it up with sand and add blue dye to create two-dimensional scenarios of various groundwater conditions. It also has ports in the back that I can open or close to drain various sections of the model. And on both sides, there's a separation that simulates a boundary condition on the aquifer. Water can flow through these dividers along their height. Most of the shots you'll see of this have been sped up because, compared to surface water, groundwater flows quite slowly. Depending on the size of soil or rock particles, it can take a very long time for water to make its way through the sinuous paths between the sediments. The property used to characterize this speed is called hydraulic conductivity, and you can look up average values for different types of soil online if you're curious to learn more. In fact, different geologic layers affect the presence and movement of groundwater more than any other factor, which is why there's so much variability in groundwater resources across the world. Like all fluids, groundwater flows from areas of high pressure toward areas of low pressure. To demonstrate this, I can set the left boundary level a little higher than the one on the right. This creates a pressure differential across the model so water flows from left to right through the sand. I added dye tablets at a few spots so you can see the flow. This is a simple example because the pressure changes linearly through a consistent material, but any change in these conditions can add a lot of complexity. In purely mathematical terms, you can consider this model a 2D vector field because the groundwater can have a different velocity, that is, direction and speed, at any point in space. Because of this, there are a lot of really neat analogies between groundwater and other physical phenomena. My friend Grant of the 3 Blue 1 Brown YouTube channel has an excellent video on vector field mathematics if you want to explore them further after this. We often draw a bright line between groundwater and surface water resources like rivers and lakes because they behave so differently. But water is water. It's all part of the hydrologic cycle, and many surface waters have a nexus with groundwater resources, meaning that changes in groundwater may impact the volume and quality of surface water resources and vice versa. Let me show you an example. In the center of my model, I've made a cross-section of a river. The drain at the bottom of the channel simulates water flowing along the channel, in this case leaving my model. If I turn on the pumps to simulate a high water table in the aquifer, the groundwater seeps into the river channel and out of the model. The dye traces show you how the groundwater moves over time. If you encounter a situation like this in real life, you might see small springs, wet areas of the ground, and during the winter, even icicles along slopes where the groundwater is becoming surface water before your eyes. Likewise, surface water in a river can flow into the earth to recharge a local aquifer. I've reconfigured my model so the pump is putting water into the river and the outer edges of the reservoir are drained, simulating a low water table. Some of the water in the river flows back out of the model through the overflow drain, showing that while not all the water in the river seeps into the ground, some does. You can see the dye traces moving from the river channel into the aquifer formation, transforming from surface water into groundwater as it does. As you can see, surface water resources are often key locations where underground aquifers are recharged. This is all fun and interesting, but much of groundwater engineering has more to do with how we extract this groundwater for use by humans. That's the job of a well, which at its simplest is just a hole into which groundwater can seep from the surrounding soil. Modern wells utilize sophisticated engineering to provide a reliable and long-lasting source of fresh water. The basic components are pretty consistent around the world. First, a vertical hole is bored into the subsurface using a drill rig. Steel or plastic pipe, called casing, is placed into the hole to provide support so that loose soil and rock can't fall into the well. A screen is attached at the depth where water will be withdrawn, creating a path into the casing. Once both the casing and screen are installed, the annular space between them and the borehole must be filled. Where the well is screened, this space is usually filled with gravel or coarse sand called the gravel pack. This material acts as a filter to keep fine particles of the aquifer formation from entering the well through the screen. The space along the unscreened casing is usually filled with clay, which swells to create an impermeable seal, so that shallow groundwater, which may be lower quality, can't travel along the annular space into the screen. Wells use pumps to deliver water that flows into the casing up to the surface. Shallow wells can use jet pumps that draw water up using suction like a straw. But this method doesn't work for deeper wells. When you drink through a straw, you create a vacuum, allowing the pressure of the surrounding atmosphere to push your beverage upward. However, there's only so much atmosphere available to balance the weight of a fluid in a suction pipe. If you could create a complete vacuum in a straw, the highest you could draw a drink of water is around 10 meters or 33 feet. So deeper wells can't use suction to bring water to the surface. Instead, the pump must be installed at the bottom of the well so that it can push water to the top. Some wells use submersible pumps where the motor and pump are lowered to the bottom. Others use vertical turbine pumps where only the impellers sit at the bottom, driven by a shaft connected to a motor at the surface. All that pumping does a funny thing to an aquifer. I can show you what I mean in the model. As water is withdrawn from the aquifer, it lowers the level near the well. The further away from the well you go, the less influence it has on the level in the aquifer. Over time, pumping creates a cone of depression around the well. This is important because one well's cone of depression can affect the capacity of other wells and even impact nearby springs and rivers if connected to the aquifer. Engineers use equations and even computer models to estimate the changes in groundwater level over time, based on pumping rate, recharge, and local geology. One fascinating aspect of deeper aquifers is that they can be confined. My model isn't quite sophisticated enough to show this well, but I can draw it for you. A common situation is that an aquifer exists at an angle to the ground surface. It can recharge in one location, but becomes confined by a less permeable geologic layer called an aquitard. Water flowing into a confined aquifer can even build up pressure so that when you tap into the layer with a well, it flows readily to the surface, called an artesian well. It can happen in oil reservoirs as well, which is why you occasionally see oil wells blow out. A part of the construction of wells that I didn't mention yet is the top. A well creates a direct path for water to come out of an aquifer, and if not designed, constructed, and maintained properly, it can also be a direct path into the aquifer for contaminants on the surface. In my model, I can simulate this by dropping some dye into the well to represent an unwanted chemical spilled at the surface. Say some rainwater enters too, washing the contaminant through the well into the aquifer. Now, as groundwater naturally moves in the subsurface, it carries a plume of contamination along as well. You can see how this small spill could spread out in an aquifer, contaminating other wells and ruining the resource for everyone. So wells are designed to minimize the chances of leaks. The uppermost section of the annular space is permanently sealed, usually with cement grout. In addition, the casing is often extended above the surface with a concrete pad extending in all directions to prevent damage or infiltration to the well. We've been talking so much about how to get water out of an aquifer, but there are some times where we want to do the reverse. Injection wells are nothing new. Deep below ground can be a convenient and out-of-the-way place to dispose of unwanted fluids, including sewage, mining waste, salt water, and CO2. But until recently, It hasn't been a place to store a fluid with the intent of taking it back out at a later date. Aquifer Storage and Recovery, or ASR, is a relatively new technology that can help smooth out variability in water resources where the geology makes it possible. Large-scale storage of water is mostly restricted to surface water reservoirs formed by dams that are expensive and environmentally unfriendly to construct. With enough pressure, water can be injected through a well into an aquifer. You can see on my model that introducing water to the well causes the level in the aquifer to rise over time. Eventually, this water will flow away, but as I mentioned, groundwater movement is relatively slow. In the right aquifer, you won't lose too much water before the need to withdraw it comes again. Taking advantage of the underutilized underground seems obvious, but there are some disadvantages too. You need a Goldilocks formation, where water won't flow away too fast, but is also not so tight that it takes super high pressure for injection. You also need a geologic formation that is chemically compatible with the injected water to avoid unwanted reactions and bad taste. Of course, you always have costs, and ASR systems can be expensive to operate because the water has to be pumped twice, once on the way in and again on the way out. Finally, you can have issues with speed. In many places, the surplus water that needs to be stored comes during a flood, massive inflows that arrive over the course of a few hours or days. A dam is a great tool to capture floodwaters in a reservoir for later use. Injection wells, on the other hand, move water into aquifers too slowly for that. They're more appropriate where surplus water is available for long durations. For example, one of the few operating ASR projects is right here in my hometown of San Antonio. When water demands fall below the permitted withdrawals from our main water source, the Edwards Aquifer, we take the surplus and pump it into a different aquifer. If demands rise above the permitted withdrawals, we can make up the difference from the ASR. You can add more injection wells to increase the speed of recharge, but above a certain pressure, some funny things start to happen. Underground formations break apart and erode in a phenomenon called hydraulic fracturing, or just fracking. Breaking apart underground formations of rock and soil has been a boon for the oil and gas industry, but just like that Texas groundwater in 1904, the regulation of fracking is mired in confusion and controversy, in no small part because it happens below the surface of the earth, hidden from public view. I'll save those details for a future video. And if you're eager to see the next Practical Engineering episode as soon as possible, you should know that my videos go live on Nebula before they're released here on YouTube. Nebula is a completely ad-free streaming service built by and for your favorite independent creators like Wendover Productions, Real Engineering, and me. It's a way for us to try new ideas and longer videos that might not work well on advertising-supported platforms like YouTube. And we're super excited to continue our partnership with CuriosityStream, a service with thousands of documentaries and nonfiction titles on pretty much every subject you can imagine. CuriosityStream loves independent creators and wants to help us grow our platform, so they're offering free access to Nebula when you sign up at curiositystream.com/practicalengineering. I know there are a lot of streaming services right now, and if you add them all up, it would be hundreds of dollars a month. That's why this bundle is such an awesome deal. You get access to 2 platforms, Nebula and CuriosityStream, for less than $15 a year. I love space exploration, and CuriosityStream has a bunch of excellent documentaries on the topic, including this one on building the James Webb Telescope that recently launched. Or watch Sam from Wendover Productions try to break the law while evading his production team in the Nebula exclusive series Crime Spree. It's a great way to support my channel and a whole host of your other favorite educational creators. Plus, it's just a good deal. Do us both a favor and click that link in the description. Thank you for watching, and let me know what you think.